So today we're going to talk about autonomy in the future of aerospace. And so here are several successes that we have seen in terms of deploying formally verified autonomous systems. Up here in the upper left-hand corner, and the laser doesn't work. All kinds of fun tech problems today. All right, in the upper left-hand corner, you can see an example of Copilot, which is a NASA Langley project that involved successful formal verification of the flight operating system. And then this is a large unmanned aerial system that has been flown several times there. Of course, there are many CubeSat operations. In the middle of the slide, you see LADEE, the Lunar Atmospheric Dust Environment Explorer. And this was a particularly successful mission from NASA Ames Research Center that deployed with formal verification all the way from the beginning of design time to runtime and exceeded all expectations for the mission. At the bottom of the slide, you can see the K-11 rover, also at NASA Ames. So this is a test bed for the DASH group, the Discovery and Systems Health group. And it is also a model for several of the rovers that have been deployed. And finally, in the upper corner, that is some of the next-gen work that Mumu was talking about. So we have used formal verification and continue to use it in the design of the next air traffic control system for conflict detection and avoidance, for resolving loss of separation events, both on board and on ground systems. However, there have been, the clicker works, some less successful missions that we would like to have operate better. And a recent example is the Exomars Chaparrally lander. Oh, okay. So does this one have a working?
I mean, it works.
Just not on the screen.
It doesn't go into the plasma screen.
Okay.
I mean, yeah, it doesn't.
It doesn't point. Well, all right. I can point manually, that's fine. All right, so anyway, recent motivation is the Exomars Chaparrally lander, and this was supposed to land on Mars on October 19th, 2016. However, while successfully descending toward the planet, the parachute deployed at an altitude of 7.5 miles above the surface, which was exactly what it was supposed to do, by the way. And at that point, it was going over 1,000 miles per hour. And then it successfully ejected its heat shield right when it was supposed to, a little less than 5 miles above the surface. However, after that, if the clicker will go, the onboard IMU miscalculated the saturation maximum period by a small amount of time, by 1 second. That wasn't a large problem unto itself. It was a simple miscalculation on board, but it led to a second miscalculation, which was that the navigation system then calculated a negative altitude. So as a result of that, we had 3 major errors go. There was a premature release of the parachute and back shell, a premature firing of the braking thrusters too far above the planet, and then eventually activation of on-ground systems thinking that the lander had landed when it was actually over 2 miles above the surface. And of course, when all of this happened, a crash became inevitable. It's like a random, there are epsilon transitions, and then yes, non-deterministic clicker. Okay, so it ended up crashing at 185 miles per hour into the surface of Mars. And this is disappointing because there were several sanity checks that could have prevented this crash from happening. They got to Mars already, and they got halfway through landing, which was all the hard parts. However, we should have been able to tell through a simple sanity check that when you are above the planet, descending toward the planet, it is not possible for your altitude to be negative, right? You are not below the surface and above the planet's atmosphere at the same time. Also, it is not possible to descend toward the planet at a rate faster than gravity, right? So if you think this has happened, you are probably wrong. Related to that, the delta or change in altitude has to be within normal parameters. The transporter has only ever been invented in Star Trek, not real life, so we cannot instantly go from 2 miles above the surface to at or below the surface in a single second. And the saturation maximum, the calculation that of course kicked all of this off, had an a priori known temporal bound. So they calculated this before ever launching the lander, but then just to be sure, they recalculated it on board. Well, okay, but there was no check that what they recalculated on board then was better than what they had launched the lander with. And that was the whole point of recalculating on board, is that they might get slightly more accuracy. So a simple sanity check could have flipped the switch to using the calculation that was stored and launched with this vehicle, which then would have prevented this crash. So these sorts of capabilities are required in order to have successful autonomous systems going forward. And so the question is, how do we fit runtime verification resources on board these frequently already flying or already designed cyber-physical systems? Because we have this interconnection where cyber-physical systems and autonomy are only going to be more and more intertwined. So we need to figure this out in order to enable autonomous systems from UAS to robots to rovers to landers to all of the other sorts of things, self-driving cars that we're attempting to deploy these days. So we asked this question. Yes?
So for that particular lander situation, did they know, I mean, not immediately, but almost immediately what the problems were, or did it take a while to kind of figure out what the sort of...
Yeah, so it was pretty obvious. Here, I keep forgetting the laser pointer doesn't work. So it was pretty obvious what caused it, right? When you have it saying that the altitude is negative and it's saying this because we have a saturation maximum period that also doesn't make any sense, that was pretty easy to find, which is what makes this really sad, because there was more of an investigation, from what I understand, into why didn't we check this than into why did it crash. Because this series of events, once we got past here and actually used this bad negative altitude, there was nothing that could be done. So, all right. I'm just going to use page down. All right, that works much better. So we're asking this question about how we can fit runtime verification into cyber-physical systems. And in particular, we were asking it in this room. So this is the N211 hangar at NASA Ames Research Center. And my colleagues there are Johann Schumann, who is standing next to the very large Swift unmanned aerial system. It has a 13-foot wingspan. It's an all-electric UAS that was used for wildfire surveillance in California. And that's Corey Ippolito kneeling next to some of his other creations. And then I'm, of course, in the middle holding the Dragon Eye UAS. So our question was, okay, how do we fit runtime verification onto all of the things in this room? And fortunately, at the time, we were like, oh, great, we found there's this whole large conference on runtime verification over here with many, many tools. It's an active research area. This year actually marked the 17th conference on runtime verification, so there's been a lot of amazing work. But the elephant in this room is that exactly none of that runtime verification technology can fly on any of those planes, which is a very big problem. In order to be able to fly on those planes, we would need something that is responsive, that is realizable, and that is unobtrusive. And there has never been such a technology. So in other words, we need something that we can abbreviate as R2U2. Why can we not fly any existing runtime verification technology on any of those planes? Well, it's because adding currently available runtime monitoring capabilities to a UAS would change its flight certification. And to quote the then Ames UAS crew chief, Doug McKinnon, who said this in a totally flat tone of voice very loudly in the middle of a meeting, losing flight certification is like moving over to the dark side of the Force. Once you go there, you can never come back. So all existing runtime verification technology would have taken us over to the dark side, and so therefore we had to invent something new in order to be able to actually add common sense onto these sorts of aircraft. And in particular, we had to add something that, like I said, was realizable. So it needed to have an expressive specification language that we could automatically monitor during the system runtime, but it also needed to be generic enough to be able to adapt to all of these different platforms and have the ability to be changed while the system is running, because these aircraft change flight modes, for example. There are different times where something might be okay or not okay, depending on the mode of the aircraft, what mission it's doing, etc. It's very important for us to be able to change and adapt while it's flying. It also needs to be responsive in real time. It needs to continuously monitor the system to detect any deviations or faults in real time and enable us to detect them early enough to actually do something about them, right? Just telling us your UAS crashed or your robot got stuck 5 minutes ago, these are not very useful things, right? We need to have some kind of real-time feedback that enables us to act effectively and save a mission. And finally, Doug McKinnon's point was that it needs to be unobtrusive. So we need to play within all of the constraints of the given system. We need to not change its functionality or already verified or certified behaviors. We need to not change anything else that's been certified on this system so we don't lose flight certifiability. We need to make sure not to alter timing or tolerances or cost or power or weight or any of the other things that have been constrained, especially when we're talking about, for example, space systems like the lander. And we need to be able to express things in the operational concepts of these aircraft, like this quote from the operational concept for the Swift. So in its operational concept, there was this timeline here, and it was accompanied by the text, whenever the Swift UAS is in the air, its indicated airspeed must be greater than its stall speed, and the UAS is considered to be airborne when its altitude is larger than that of the runway. So you can see on this timeline, we are progressing from left to right in time. We have some command for takeoff at a time when we are on the runway, when our altitude is equal to that of the runway. And then sometime after that, we are airborne, so our altitude is greater than that of the runway. And during this airborne time of the mission, we need our indicated airspeed to continuously be greater than our stall speed. So the question was, how do we create something that unobtrusively, responsively monitors exactly this? And we want to be able to say something like, it is always the case that the altitude being greater than that of the runway implies the indicated airspeed is greater than the stall speed. So the way we do that is with something that we called mission time linear temporal logic. So because operational concepts are nearly always drawn in timeline fashion, we will use linear temporal logic, or the logic over timelines. And in this case, we can be even smarter about how we use it, because these are all missions with a priori known temporal bounds. A UAS has a short battery life. In the case of the Swift UAS, it can fly for a maximum of 6 hours, and that's only if you don't do anything particularly fancy with it. In the case of the Dragoneye that I was holding, that had the shortest flight time of only half an hour max. So we have these convenient bounds that we can stick on temporal operators in our logic, and it allows us to reason about and express very intuitively anything that's drawn in an operational concept timeline. So for example, we can say that always between times 2 and 6 that P is true. So we have times 2 through 6, and we can see that P always holds, and we don't care what happens in the other timelines or time steps. We can say that eventually between times 0 and 7 we'll see a P, and in fact we see one here. We can say things like between times 1 and 5 we have that P holds until such a time that Q holds. So starting at time 1 we have P holding until such a time that Q holds. And finally we have the release, also known as the button push operator, and this allows us to say things like P releases Q, or pushing button P releases thing Q from having to be true, which essentially means that thing Q has to be true unless and until we choose to push button P, at which time we don't care what the value of either of these are. It turns out this is expressive enough to be able to capture the things we needed to say, at least the temporal things we needed to be able to say about all of the autonomous systems I've showed you so far, and we can reason about it efficiently. So for every temporal logic formula, we came up with 2 ways of encoding this formula for runtime verification. And the first way is the asynchronous or event-triggered way. So this is when we evaluate the truth or falsity of the formula with every new event input. We have two valued output of either the formula is true or false at this time. We resolve this as early as possible. So for example, if we have a formula that says it's always the case for 5 time steps from now that P will be true and P is false right now, we don't have to wait 5 time steps to know that this is going to be false, right? We could say this is false right now, and that's very helpful because then we get the answer earlier, and anything that depended on this answer can be calculated earlier, can be deployed earlier, etc. So for each clock tick, then, we resolve any discrepancies that we might have, that we have enough information to resolve in the current time or perhaps in the past, because we're reasoning over future timelines. So it might be the case if we have, for example, globally or always from now to 5 time steps from now P, and P is true now, then we don't know whether or not that is going to hold. And in fact, we can't know that it holds for 5 time steps. So 5 time steps from now, we will be able to say, okay, at the time step that I'm standing in right now, right, we know that it was true. So we can resolve that at that time. To give you an idea of what this looks like, if we have this sensor data at the top of the slide, and we have the formula always for 5 time steps, the pitch is greater than 5 degrees, then we can see this middle line here represents the pitch being greater from 5 degrees. And we can see at time step 0, it's false. So we know that this temporal formula is going to resolve to false at time 0 without waiting to be able to evaluate it. For the same reason, we know it's false at times 1 and 2. At time 3, you can see the pitch is in fact greater than or equal to 5 degrees. So we don't have any output for this runtime monitor. And we don't have output again until time 8, at which time we know that it was true at time 3. Okay? Similarly, we can resolve steps 9 and 10. And then at time step 11, we know, all right, from times 6 through 11, it was false. And we're resynchronized up with the current time. We also, for the same temporal logic formula, encode a synchronous observer that runs at the same time in parallel with the asynchronous observer. And this is a time-triggered observer. It can update continuously. Because of that, we get 3 valued output, true, false, or maybe, because of course we can't always know the result of the formula at every point in time. We do this because it has a very small footprint. We can almost get this verdict for free. And while we might get something like maybe, that's still an incredibly useful output because it provides a sort of pulse that the runtime monitor is still operational. Like, I'm here and I know that I don't know. That's an important thing to know, yes? And so we can make sure that the runtime monitor is working, that it definitely knows whether or not it knows the answer to a formula, and then be confident that through the asynchronous observer, if we didn't know immediately, we'll get an answer in the future. To give you an example of what this looked like, for this formula here, we have always for 5 time steps, the altitude needs to be greater than 600 feet, and the pitch needs to be greater than 5 degrees. Then we can see at every point in time we get an output, and because pitch greater than 5 degrees is false initially, then we know they're false. Then we have altitude is not greater than 600 feet until time step 10, at which case we get a maybe, because they're both true at time step 10, but we can't know if they're going to hold for 5 time steps from now. So in this way we get this heartbeat as output. And we can combine these in a compositional fashion with other building blocks. One building block that we found to be particularly useful is tiny Bayesian networks. So here we can encode, for example, probabilities that we have suffered a certain fault, and we can hook these up in tandem with the temporal logic monitors. And this allows us to make more intelligent decisions and disambiguate faults in the system. So to distinguish for those of you who are familiar with BayesNets, we're specifically talking about just the very most basic Bayesian health nodes. We're not talking about dynamic BayesNets or anything else that would involve temporal properties. The idea is to hook up something very lightweight that can still evaluate in one tick of the system clock, but that can be combined with our sensor filters and our temporal logic monitors to produce a richer landscape of output that would enable us to effectively add runtime verification to any system. So in short, R2U2, our realizable, responsive, unobtrusive unit, currently combines these three major building blocks for our specifications, which we also call observation trees. We have signal processing, or the filtering and preparation of sensor readings. We have the temporal logic observers, the asynchronous and synchronous observer for every temporal logic formula. And then we have our tiny Bayes nits that enable us to efficiently make decisions as to whether or not, for example, we are probably seeing the occurrence of a fault. An example, a real example of what this looks like is here. This is an observation tree that we used in this paper and in some other ones to disambiguate the health of a flux gate magnetometer during a real flight test at NASA. So there was a flight test where NASA took a UAS to Costa Rica, and this was a very overbooked flight test, like most of them. So they had people working in shifts, testing 24 hours a day, recording important flight test data. And when they got to Costa Rica, the flux gate magnetometer suffered a fault. Everyone knew this. It was not a big deal. They reset it and checked everything out. Everything seemed fine, and they proceeded with the flight test. But then after they started, they noticed that the data was a little bit wonky. However, any individual snapshot of the data that they looked at seemed fine. So, long story short, it took the engineers 48 hours working round the clock to disambiguate that the factory settings of the flux gate magnetometer had been set wrong. So when it reset itself, it was actually sampling data at a slightly different rate than it was recording it. But because of the way that they were doing the flight test, getting an answer that looks right for now, that looks marginally differently from the one you got 15 minutes ago. It's very not obvious that you're looking at the data from 15 minutes ago versus now. So that was difficult for humans, but this observation tree actually picks out that fault in real time. So we take in here in the peach the values of the sensors on board and the flux gate magnetometer data along with other data to compare it to. Then we filter it, and we have this row of Boolean testers where we compare it to certain bounds that enable us to fill out the values of the Boolean variables that are in our temporal logic formulas here in the teal. So we wrote one temporal logic formula to describe each of the 6 symptoms that a flux gate magnetometer might possibly display, indicating that it had a fault. And then you can see we have a structure above with 5 health nodes, Bayesian health nodes, that describe the 5 faults a flux gate magnetometer can suffer. So for example, this fault here on the left is probably the fault we are suffering if we see these 2 symptoms. However, if we see this symptom and this other symptom, it is probably instead the second fault, etc. Right? So we can set up R2U2 in this way and therefore effectively disambiguate between different faults of the flux gate magnetometer, picking out the real faults in real time when we ran this on NASA's recorded flight test, pretending we were running on board. So in short, we want to be able to encode all of these things very easily. We want to encode, for example, sanity checks about rates. So you cannot, for example, fall faster than gravity toward a planet. It would have been useful for the Chaparrally lander to know that. Also ranges, so when you are in descend toward the planet mode, you cannot be underground. Your altitude cannot be negative. These 2 things are also highly inconsistent. You can also think of a common error that we get when flying UAS, a range error, is we tend to depend, for example, on the laser altimeter. However, you can easily pass out of range of the laser, in which case you need to not trust that altitude and switch to a different source. We want to reason about relationships. For example, if we deploy the parachute, then we can predictably know that a short amount of time later, we will see a decrease in velocity. The same thing happens, for example, when we deploy the braking thrusters. This will result in a decrease in velocity. We know how long this will take and what magnitude decrease in velocity we will have, and we can use these a priori known relationships to do sanity checking over what we think we are measuring and therefore detect faults in our sensors. Also, there are several control sequences that we have programmed into various aircraft and spacecraft. We want to sanity check that they happen in the a priori known order. For example, with the Chaparrally lander, we first jettisoned the heat shield and then we detached the parachute. So these things happen in a predictable order and with a predictable time displacement. And finally, we have things like consistency checks. It should always be the case that your autopilot and your flight computer agree on what waypoint you're at, or where you are, or other vital pieces of information about the operation of your aircraft or spacecraft. If they don't agree, one of them is wrong, right? So this is the kind of thing we need to be able to detect. In order to be able to do that, and in order to be able to do that first on board the Swift, which only had an FPGA that we could modify. We were not allowed to touch any of the flight computers on board that system. We came up with an efficient hardware encoding for both the synchronous and asynchronous temporal logic monitors. We did this, for those of you who are familiar with runtime verification, in a slightly different way from the usual automata theoretic approach. So rather than constructing a state machine and progressing to the next state every time an event occurs, we decompose the formula into subformulas, and then we hook up the output of the subformula into higher level formulas. In this way, we can be very efficient about the way we store it on the FPGA. For example, a subformula that occurs more than once in a formula or occurs across different formulas that we are monitoring can be stored once, and then the output can be reused. And we also graduated to space systems from the Swift. So we started looking at how can this be deployed on things like rovers or landers or CubeSats or this guy. So as promised, this is Robonaut. He is the humanoid robot on board the International Space Station. He started out as just a torso, but then they added these very wonderful, long, octopus-like legs afterwards. And so I'm holding one of them and his twin in NASA Johnson Space Center in Houston. And he has amazing capabilities for interacting safely with the human co-occupants of the International Space Station. So he moves around, acts as an intelligent co-pilot and assistant, and can do things like hand astronauts tools or help with repairs. He navigates by, on the bottom of his leg there, he has a camera and then a grasp technology where he can see in the middle of the camera and then grasp onto the different rails around the International Space Station that humans hold onto with their hands or hook their feet under. But he has a minor problem. Okay, which is that his joint, which you can see right here, his knee, and here is that same joint in my lab along with his brainstem, and that is my PhD student Brian, who is programming this knee here. His knee has a fault mode that was unanticipated and emerged after he arrived on the International Space Station. So in particular, he can get his legs into a little bit of a tangle and then not be able to disambiguate in which way he got there. So he is unable to safely untangle himself because he might have gotten there through sensor drift or through too much force being applied to his joint. And of course, you want to select the correct mitigation mode and not accidentally injure a human by assuming it's too much force, but in reality it was a sensor drift error. So anyway, in order for him to resolve this and to unstick himself when he gets caught in a certain position on the ISS, he calls ground control in Houston and asks them to untangle his legs. And of course, the good people at ground control have nothing on Earth better to do while controlling all things in space than untangle the legs of a robot. So they're quite annoyed when he makes this call and have asked us to please help. So his knee joint arrived at our lab at Iowa State University this January, so we could help with this. Yes, that is a puppy cage, and yeah, apparently Congress thinks you can get a PhD in engineering, but would be thwarted by a puppy cage being around a knee joint. But anyway, so so we are here trying to figure out exactly how we can disambiguate this with R2U2 on this small credit card-sized FPGA that controls the knee. So the challenge is fitting into there the ability to look at this question. So this is a diagram of how the absolute position sensors work in R2's knee. So he has this circular knee joint that you saw sitting in my lab, and then there's a calculation over these sine and cosines here that you can see juxtaposed on his knee joint here. And he attempts to figure out what position his knee is in by a unique calculation that's done very, very efficiently across these. And so when he gets it wrong, then he has a 30-degree shift in where he thinks his knee joint is actually rotated to. And this is one of the things that creates the fault. So just like with the Chaparrally lander, this is not something where we have to be precise down to thousandths of a decimal place, and if we have a small floating point error, we're going to be a little bit off. We're going to be 30 degrees off, right? So this is not close. And we need to disambiguate between whether, for example, his absolute position sensor 1 has sensor drift, whether absolute position sensor 2 has drift and needs to be reset, or whether he's experiencing torque on his joint. And so here is a video that will hopefully work, demoing our recent success in deploying R2U2.
This demo showcases the capabilities of R2U2 on the Robonaut2 platform.
That's Brian speaking.
On the controlling PC, a user generates a set of configuration for R2U2 that include the atomic checker conversion functions, mission time linear temporal logic formula, timestamp width, and operation mode. All these values are compressed into a binary configuration format for interpretation by R2U2. After starting the robot, the configuration file is sent to R2U2. We use a serial line for this, but any communication with the FPGA can be used. After receiving a start command, R2U2 begins returning monitor status in real time. This can be monitored and analyzed from the brainstem.
So you'll see another PhD student
In this
typing
demo,
over
on the
here.
left side of the screen, we see the control console used to configure and read R2U2. In the center is the SMT scope displaying the output of the absolute position sensors 1 and 2, as well as the encoder position of the joint test article. Our first test case utilizes 2 atomic checkers and 4 temporal reasoning instructions. The temporal reasoning is generated from a file, shown on the console, which defines the final output as the conjunction of the atomic checkers. The atomic checker configuration, seen on the console, define Boolean logic propositions over the system bus variables. In this configuration, we see the sum of the absolute position sensors being compared. Specifically, we are checking if the sum is greater than 40 or less than 80. By summing the absolute position sensors and comparing the resulting value, we can check the phase between the position of the sensors. This corresponds to force on the joint. Now the configuration is compiled, sent to R2U2 over the serial link, the start command is sent, and we begin receiving verdicts from the real-time monitor. At each time step, we see the verdict of the individual reasoning instructions generated by our formula. These instructions correspond to PC 0 through 3, shown on the right-hand side of the screen. With no force on the joint, all the values are true. R2U2 is reporting that we are within our defined limits. Now we apply force to the joint. When this torque violates our configured limits, R2U2 begins reporting false.
So you can see the values updating here and how we're not always at the current time, especially in the next part of this demo, because again, these are future time formulas, so we can't always know the verdict right now. Here.
We will now demonstrate the effects of a temporal operator.
Right.
R2U2 can be reset and reconfigured on a running system, and we'll take advantage of this.
This is a unique feature of R2U2. So while other people have attempted to put runtime monitoring on board FPGAs, you always have to entirely resynthesize, so this cannot be changed during a mission, which is a very useful thing.
By adding a globally 0 to 3 in front of our conjunction, we verify that the torque on joint remains within our set limit for the next 3 time steps.
And then when pay runs it here, you'll be able to see that sometimes we know the verdict immediately. We always report it as soon as possible. However, sometimes we can be up to 3 time steps off if our globally operator is evaluated to true.
At startup, we see a 4 time step delay in the evaluation of the globally operator due to the causal information required.
You can see the delay of 3
However,
time steps here.
When the conjunction becomes false due to excessive force on joint, the globally becomes false immediately due to the sufficient information available. Additional MLTL operators, such as until, Boolean operators, such as negation, and Boolean checkers are available, and work continues on integration of additional sensors from the RoboNet bus.
Okay. So essentially here we're doing more than simply runtime monitoring or returning the output of a single formula, but we're taking runtime monitoring and we are lifting it to temporal fault disambiguation, also done in real time. So this is a unique feature of R2U2, and we actually got mentioned in a talk on Tuesday at the conference on runtime verification, where Gilles Rozier was presenting this paper, and he blurted out during the presentation, R2U2 breaks our taxonomy. It is entirely application driven. This was meant as a bit of a constructive criticism. He said it with a smile on his face, but I took it as a compliment because that's entirely the point, right? So this is the runtime verification technology that is driven specifically by being able to actually fly, to complete an application in real life. So apparently we don't fit in very well at all for their taxonomy and for classifying all of the runtime verification tools, but we fill a very unique niche in this research community. And in particular, in order to be able to do that, again, we're running, for example, on things like the space left over on a credit card-sized FPGA. And in this space, we need to be able to we need to be able to fit all of our reasoning units. We also have the option of running in software, for example, on a separated flight computer. So there are hardware, C and C++ implementations of R2U2. This enables us to run on a variety of platforms, specifically if only one of these implementations is allowed to run under the flight certification of the vehicle. If, for example, all of them are allowed to run, then we can have a strategy for voting to have additional assurance that our runtime monitors have not themselves suffered faults. So each of these implements the same algorithm, but very differently. So in FPGA and hardware, in a C program that essentially emulates what the FPGA does, but in software, and in an object-oriented algorithm in C++. So in theory, these would fail differently, and probably only one of them will fail at any one time, thus giving us a three-way voting algorithm for ensuring the health of the system health manager. We have gone on to then looking at, all right, how do we fit this into even more constrained spaces and know a priori whether we are going to fit on something like Robonaut 2 before we go and try that. So in our latest work that we are currently writing up and submitting, we have looked at the problem of resource estimation and then enabling options in the encoding algorithms so that we might be able to, for example, trade off resources that are more constrained for resources that are less constrained. The idea behind this would be to be able to take something like the space left over on R2's FPGA and be able to estimate, okay, if we have the sensors we want to reason about and the monitors we want to encode, how many resources on that FPGA? For example, on the right-hand side of the slide, you see a graph of time step width here. What time step width would we be able to encode, and how big would that be? So we can then make intelligent trade-offs between what we want to monitor, how many monitors we want to put on the system, and in the future, perhaps more ways of encoding these monitors so that we can trade off a resource that we have less of for one we have more of, and make sure that we can truly maximize how much we can say, how much common sense we can add to a platform in the space left over and in the resources we're allowed to utilize. We're also looking at questions like how do we make decisions with incomplete information? And in particular, in a lot of runtime systems, for example with the UAS, as like with Robonaut, right, there is a small a priori known number of mitigation actions that one could take, right? Robonaut is essentially choosing between 3 actions that he could take. Similarly to a UAS, you might have, if something goes wrong, you either decide, all right, this is critical and I'm going down now and so I just need to do that as safely as possible. Or you say, okay, there's a fault and I will probably not be able to successfully complete my mission, but I can run my safe mode plan where I abort the mission and then fly home or to my designated safe landing place where there's a mechanic. Or you can say, okay, there's maybe a fault or no fault, but it doesn't really matter because if there is a fault, it's not sufficiently critical that I can't complete my mission, so I'm going to choose to complete my mission. And these mitigation actions have a priori known lengths of time to launch, right? So there's a known amount of time before, for example, you would need to look to launch your safe mode plan to land and call a mechanic. And you have to decide whether or not you've suffered a sufficiently critical fault that much time before deploying that plan. So at that time, because we're reasoning over future time monitors, you might not always have all of the information to evaluate whether you've suffered a fault. But, for example, you might have some of the variables. So the idea is that in the control flow here of R2U2, we could combine model prediction with runtime verification to have model predictive runtime verification, where we have the environment being sensed, and we propagate the sensor values through our Boolean testers into our encodings here. So we have our atomic propositions that are filled out from Boolean testers over the known sensor data, and we can evaluate then with our future time monitors whether some fault has occurred. However, if we hit that temporal bound where we need to make a decision of whether or not to take a mitigative action, we can then choose to use model prediction in a parallel execution path to fill in the most probable value of any information we don't know. And in this way, we can make decisions in time to be able to mitigate problems using the maximal information we have available in the system and then a best guess as to anything we don't currently know. So using our model predictive runtime verification in 2 examples here. At the top, we have an example with a future time operator where we want to know if some A1 happened and A0 happened in the future. So the green is the real sensor data. The yellow is how R2U2 works with no prediction. And you can see that sometimes we have a bit of a delay. Like for example here, we can't know that this happened until a later time when we have enough information to absolutely know that we experienced this dip in the green line here. But if we add model prediction to fill in the values of the variables we don't know in our logic monitors, we can then detect that something is going to happen even before it's actually happened, in enough time to take a mitigation action. So this leads us into the next steps. We are looking at a whole bunch of other different expansions from here, and in particular, now that we've graduated from air to space, this opens up a lot of avenues for looking at things like the problem of radiation and running on non-radiation hardened hardware in space. So when you have something like Robonaut 2, we could suffer radiation errors, and we are running on commercial off-the-shelf cheap components that NASA has stocked in there. They are not rad hard. So then how are we able to check both the checkers and other pieces of hardware and software on board the system in this radiation challenged environment? So this is one way where we are hoping to come up with some more creative schemes for checking the checkers, for running the runtime monitors in parallel, for interesting voting schemes, and for looping in other ways of figuring out how to detect radiation problems using runtime verification. We also have the very interesting problem of swarms. So swarms are complicated to reason about, but give you all kinds of additional information that you can use to more intelligently decide if something has gone wrong. And in particular, you might have observations that are external to your own ship or the system you're running on that you can incorporate into the data on board your system to be able to make decisions about whether you've had a fault. So for example, a rover on a planet is usually watched by a satellite and might be able to use additional information from the satellite to back up its own assessment of itself. CubeSats are launched in swarms. UAS, especially on other planets, usually work in groups and can observe each other. And then the question is how to effectively incorporate data from these external observers and then do that in a reliable way where you don't suffer from, for example, communications errors. We're also looking at different resource constraints and how to accommodate those. So we're expanding our resource estimation tool, making this an online tool with, for example, a GUI, so that if you want to deploy R2U2, you would be able to go to our website to be able to enter the sort of runtime monitors you might want to run, know how much in terms of resources those might take, and then look at, for example, how you could encode those differently. And of course, there are many more directions. So we would like to do better diagnostics and better prognostics through intelligent system health management. I also had some very interesting conversations with some of you earlier this morning about how to do more intelligent sensor fusion. How do we update glass cockpits so that we can better prevent some of the accidents that we've seen happening when we have things like iced over pitot tubes and pilots that don't have the temporal information available to them to be able to disambiguate between important faults. How do we link SHM, for example, to planning and to plan execution so that we can be more intelligent about executing plans that are aware of faults that might have happened, for example, with airspeed or velocity sensors, but without complicating the plans and causing them to run slowly or not be responsive in real time. And then this very interesting problem of explainable system health management. So how do we enable an intelligent co-pilot to not just say, you might not want to look at that sensor, but to say, why not, right? You might not want to look at the altitude from the laser altimeter because we have drifted out of range and it now disagrees with other altimeters. How do we give some kind of feedback like that? And interestingly, how do we enable, for example, a human to ask questions? So in the future, if we expand R2U2 to other subsystems on Robonaut 2, could we have the astronauts be able to ask R2 different questions and then he could answer from what he has been monitoring about himself? So I will leave you with a summary of R2U2, and I'm happy to answer any questions.
Are there any types of specifications that are not easily formatted in how you've sort of described the mission in LTL?
Oh, sure. So one of the actually big debates that we had at the Runtime Verification conference this year was, what should a specification language look like? How expressive do you need it? Because there are some extremely expressive specification languages. There are some one-off specification languages for particularly stream-based runtime monitoring that are entirely rich programming languages unto themselves. So they allow you to create monitors for all kinds of very complicated things, solve partial differential equations. We don't do that at all. But there is, of course, the trade-off between expressibility and computation, right? So there is a huge branch of RV at developing more and more and more expressive specification languages, programming languages for runtime monitors, etc., so that you can express these incredibly rich, intuitive, complicated things that people come up with and be able to monitor for those. But then you have the challenge that those don't run in real time, and they really, really don't run embedded on something. So people are running these, on their local academic supercomputer, right? And then saying, okay, well, using my supercomputer and unlimited time and unlimited power, then I can monitor this property about a system execution, right? So it's striking that balance. And when we look at the types of things that have taken down aircraft or spacecraft, they tend to be things like what I exemplified with the Chaparrally lander, right? Where there's something that is dead obvious in the string of things that happened. We might not be able to, for example, recalculate the saturation maximum very efficiently in one tick of the system clock, but we can definitely tell you that it shouldn't result in a negative altitude, right? That has a constant time. So there are a lot of constant time checks that we can do that would still cause us to be able to at least intelligently mitigate faults that we've seen on real aircraft and real spacecraft.
Do you ever get into situations where you sort of had a couple of different specifications you were testing on different do you have them on different time scales, for instance?
Oh yes, that's an excellent question. So we actually get this a lot. There are, of course, other temporal logics that are close to mission time linear temporal logic, but allow you to do things like, for example, in STL or signal temporal logic, you can have real numbers for the temporal bounds instead of integers. And people argue, well, because you might want to know the temporal bound to like 100th of a second or something, and so you should be able to write that. But the really nice thing that we found about saying we'll use integers is they're unitless, and you can map them to, for example, different granularities in time. And then you can have these really nice, more generic, more reusable specifications that effectively disambiguate faults if they have sufficient temporal information. And then you can, for example, change what granularity of time you might monitor them over to, for example, utilize more or fewer resources if you're limited in that way. And that was one of the things that the graph here is showing is there are some different granularities of time, for example, the timestamp width that we can vary, and then it changes the resources used to encode that monitor. It also might make sense, right? Different sensors sample at different rates. So you might want to have a generic specification, for example, the one I showed about altitude, right? But then depending on which altimeter you're getting the altitude from, you might want to have a different sample rate because they measure at different rates, right?
But if you had sort of two different sensors on two different kind of sampling rates,
Yeah.
let's say one is even an order of magnitude different. If you were to sort of check them, the overall satisfiability, I guess.
Yeah.
How do you reconcile that difference in timescale and difference in
Yeah, that's a great question. So you have to make a decision, right? So you can either say, well, I'll just, sample, for example, at this rate, and I will just take the most recent value from each sensor that I got at this rate, right? Or that's what we're doing right now. There might be other ways to do something more intelligent, but then when you get into things like computing averages or medians or stuff, then you get into some more temporally complex, computationally complex things that we're attempting to avoid so that we evaluate very quickly. And like I said, we're generally looking for things that are not close to something. We're looking for is R2's knee 30 degrees off, right? Is the Chaparrally lander's altitude 2 miles off, right? So, so using slightly old sensor data doesn't really affect our ability to detect those sorts of things.
Any other questions?
Yeah.
So what does NASA usually use for some sort of fault mitigation in their systems?
That's a great question. So there are a lot of experiments on that, and I included this here because, for example, the K11 rover here is actually a testbed platform for answering exactly that question. So there have been several different diagnostics and prognostics engines at Ames and Langley that have been tested on this rover, and then the same algorithms can get tested in 3 space on this UAS. And they're working it out. There are several different candidates, and then they've basically been mapping a configuration space of a whole bunch of these that where they see what the cost is in terms of computation time, how responsive they are, how good they do it at diagnostics and prognostics. So yeah, the answer is there isn't a typical one. There are probably at least 10 different technologies that they've tried out on this system just recently. And then they each have pluses and minuses, and none of them are flight certified at this point.
Are there any plans to include temporal logic detection, fault detection? Are there any plans?
Yeah, well, so to a limited extent, some temporal logic work has been deployed on, for example, some of the rovers that have come out of NASA JPL. So generally they've used the spin model checker to check during design time different properties of the rovers, and it's my understanding that then some of those checks made it into deployment of those rovers. And then we have worked with NASA, and of course Johan and Corey are still at NASA, and then we have a collaboration funded by NASA now through Julia Badger, who is the head of the Robonaut 2 project and also my program manager for this project. So there are several people that are at NASA who are using this sort of thing. So there's definitely plans, of course, to put it on Robonaut 2. But then, for example, Johan has continued work putting this on various UAS. And I have in another grant worked with another part of Ames Research Center looking at putting different temporal logic monitors on their different UAS. And then we have another grant through NSF where we also are collaborating with NASA looking at the UTM problem, so the UAS traffic management problem. And as an integral part of that solution, we're looking at how to integrate some runtime checks into some of the different mitigation strategies we might have for UAS. So that is very preliminary at this point, but it's another thing that we're looking at in collaboration with NASA. Yes.
How did you classify your section of code, whether you need to implement your code into C inside FPGA or just into FPGA? Because your FPGA architecture contains C or C++ inside. So how did you divide whether you need to implement inside C or into?
Yeah, that's a good question. A lot of it is where do we fit? So certainly in most of these systems we have looked at, for example, with the Swift, we didn't have a whole lot of choices. They were like, you will fit exactly here. So that's what we did. And then, for example, in R2's knee joint, we initially didn't fit anywhere, so we had to come up with different ways of encoding and estimating the resources and being smarter about what resources we used. And so now we are finally at a place where R2 has been recognized, and some systems might be designed with the ability to run it in mind. And so then that will become more of a decision that we will need to make in the future. But so far, we haven't faced that so much. It's just been fit in the space left over, and there's sort of an obvious place where we could possibly fit something.
Was it easier to combine C code with FPGA rather than just implement all the code in FPGA?
Was it easier? I didn't personally do it, so I'm not sure. Most of that work was actually done by Pei Zhang, the PhD student who was typing in the console on the side. I'm also not an FPGA encoding expert, so that part is a collaboration with Joe Zambrino and Philip Jones, who is in the audience right there. Did you want to say anything else about the FPGA encoding?
I guess, short answer in general, if you put something in the FPGA, it's typically going to be a hardware design using VHDL. Usually if you're going to run C, you're going to have some type of microprocessor running someplace. So some of the FPGAs on Robonaut 2 have no microprocessor. So your only option is to throw it into VHDL if you don't want to corrupt the code or disturb the flight certification of the code running on a separate flight computer. So into the Robonaut 2, we have the R2 tube not on the flight computer. It's on the FPGA that actually is out in the raw sensor data.
And did you import all the libraries to use your code inside it?
So it's a hardware design, so it's basically AND gates, OR gates, stuff like that. So it's not really libraries, it's more this functionality. So you have equivalent functionality, so you can take a C version of it or the hardware version, run a regressing test, and get the same answers.
Yeah. So in the future, hopefully we'll have more of a choice as to where we can deploy. But unfortunately, it's often the case that runtime verification comes as a last resort. So you do something like put the robot on the International Space Station and then realize it has a problem. Or launch the UAS in Costa Rica and then realize it has a problem, right? And it's at this point that, I get this call saying like, how, what can we do in terms of adding runtime verification to our already running existing system? And then we don't have a lot of choice as to where we would possibly fit.